Namaskar friends. Friends, myself Dr. Ashwini Kumar Gupta. Today I'll be starting with the lecture 11 in which I'll be taking up to a absolutely fresh topic in class 10th. That means in lecture 10th I had finished the isomerism series. I hope you might have understood everything. Then today I'll start with a totally new topic, fresh topic, today's lecture. That is reaction intermediates. So what do you mean by reaction intermediates or reactive intermediates, basically speaking? What do you mean by reactive intermediates? Reactive intermediates, take for instance, suppose if you want to go from a particular place A to B, A to B. Now what happens? You directly don't reach to the point B. First you go from point A to some X, then from there to Y, and then that connects to B, right? So these point X and Y are nothing else, they are essential points where you have to pass through them and then only you'll reach to your final destination. So you can say these point X and Y are nothing else but reactive intermediates. They are reactive intermediates, and at that particular place X and Y you don't stay permanently, you stay only for a few seconds, do whatever you have, only wait for a few seconds and then you go and go towards your final destination, right? Go towards your final destination. So your heart, for a very short time you are there at that particular place. So today I will explain what you mean by reactive intermediates or reactive species. Basically speaking, they are reactive species which are formed during a chemical reaction. Whenever a chemical reaction takes place, there are certain type of species which are formed before a product formation takes place, before a product formation is there. Now what is that? Reactive intermediates or reactive species. ठीक है? Reactive intermediates. Intermediates or reactive species. Now, what do you mean by reactive intermediates or species? They are the species formed before the product formation, before the product formation. Why these species are formed? First thing, due to heterolysis. Heterolysis, I have told you. What do you mean by heterolysis? Heterolysis means breaking of bond. Heterolysis of a chemical bond. Now what do you mean by bond? Bond is nothing else but sharing of electrons. That means two electrons are involved in the bond formation. So heterolysis of a bond. During a heterolysis of a bond. Okay? Now these species formed are short-lived. They are not only short-lived but they are highly reactive. They are highly reactive and short-lived and highly reactive species. So a product takes place via these species. Now, electronegative element. Electronegative element. That means electron withdrawing group. Strong electron. So these are the two electrons where the bond is formed. Suppose now this G will pull electrons itself. So two things can happen. Either the electron which is there with the carbon atom goes along with G. That means when G pulls the electron, it can also pull the electron which is there with C, right? Then it forms one type of a species. And when, if at all, the bond breaks, it takes away only its own electron. It does not take the electron which is bonded to C, which is a part of C. So that gives another type of species. So now I'll tell the name of those species. So, and there are many more other types of species also formed, right? First make a note of it. Reactive intermediates. Okay? Now, there are different types of reactive intermediates. I'll show it by RI, right? Take for instance carbocation, carbanion, then free radical, then carbene, then you can say benzene, then you can say nitrene, right? So carbocation, carbanion, free radical, carbene, benzene and nitrene. So for us primary importance are these three: carbocation, carbanion and free radical. So we will be concentrating on these three species, right? Well, these are also important, but as and when it comes, I will explain you. First, our primary importance is these three. Now, what do you mean by carbocation? Wait, okay. So I'll take another slide. Right. Carbocation. As I had told you, there was C and this is bonded to some G. Right? When the bond breaks and the electron of carbon also goes along with G, right? There is a bond, the bond breaks. Okay? So now the electron of G is this, and when the bond breaks, the electron of carbon also goes along with G. So now the carbon is left with only 3 electrons. Fine. So it is a shortage of one electron. So it is positive charge. Right? So it is positive charge. So a positively charged species. So you can say that when an electronegative element results in a hydrolysis, then results in formation of carbocation, where the electron of the carbon is pulled by the electronegative element. Right. So I will say, suppose this is C. Take for example 4 valencies of C. This. Yeah. Now. See, this is G. Fine. Right. So this is known as carbocation. You can say carbocation is nothing else, means it is also an electrophile, because electrophiles are positively charged. Okay. So can I also say they have, if they are electrophile, then obviously they will react with a nucleophile. Then it has 3 bond pairs, that means it has 6 electrons. That is 3 bond pairs it has. 6 electrons. Then it has a vacant p orbital. And fourth, basically speaking, it has a planar structure. Carbocation has a planar structure. Fine. So this is nothing else but carbocation. Now, there are some different types of carbocations, like alkyl carbocation, Fine. Then allyl carbocation, then vinyl carbocation, fine. Then aromatic carbocation, carbocation. Then you can say even phenylic, sorry, not phenylic, benzylic, carbocation. Right? Take for instance alkylic carbocation, in the sense you can say CH3 plus. Then allylic you can say CH2 double bond C single bond CH2. This is nothing else but CH, right? So this is positive. This is allylic. Phenylic in the sense C double bond C H2. This is vinylic. Aromatic carbocation means it can be right. Aromatic carbocation, benzylic carbocation, benzylic carbocation. Fine. Right. I'll take a new slide. Yeah. We shall see the order of stability of these carbocations. You can say first we'll start with alkyl carbocation. We can say a tertiary carbocation is more stable than primary, than secondary, and then primary. Tertiary carbocation means it is attached to 3, and this is secondary, it is attached to 2, and this is primary. This is, yes. Tertiary is more stable than secondary, which is more stable than primary. Fine. But why? Because alkyl groups, which are nothing else but electron donating, so since they will be donating electrons, so the positive charge of carbon will be getting more and more dispersed. So due to dispersion of positive charge, dispersion of the positive charge leads to stability. Fine. Because it will go more the amount of electron on carbon atom, more the positive charge will decrease. The decrease means it will become more smaller and smaller. Therefore, that will lead to more stability. So I can say in tertiary there are three R groups, 3 alkyl groups attached. So the electron flow will be most as compared to primary, and methyl it will be the least. So this is the order of stability in there. Now take for example one more. By one more means also we can explain. That means I can say, since it is an electron donating all, I can say it will be plus inductive effect. That means a plus I effect, due to the plus I effect of alkyl group, that results in stability, and therefore that is also one of the reasons for its stability. Now second happens to be hyperconjugation, which I have taught you. Hyperconjugation. Take for instance CH3 C CH2 dash H dash CH3 and plus. So can I say this will go here? So this will give CH3, C double bond, CH2, and then sorry, CH2 double bond, and then this is CH3. Fine. So like that I can say 3 alpha carbon atoms. I can say this is one alpha carbon atom, alpha carbon atom, alpha carbon atom, right? 3 alpha per alpha carbon atom will give 3 structures. So 3, 3, 6 and 3, 9. That means 9 hyperconjugating structure. This is a no bond resonance, right? Hyperconjugation is also known as no bond resonance. So 9 hyperconjugating structures. So more the hyperconjugating structures, more is the stability. So one of the reason for it is inductive effect, the other is hyperconjugation, right? Therefore, now we'll go for allyl carbocation. Allyl carbocation is CH2 double bond CH dash CH2. Allyl carbocation. Now allyl carbocation is also very stable. Actually, it is more stable than alkyl carbocation. Alkyl carbocation. Allyl carbocation is more stable than alkyl carbocation. Now why? Because if we can see in allyl carbocation, there can be a resonance. CH3, CH dash. So can I say like that? CH2 dash CH2, right? So this will be, these two structures will be in resonating. They will be in resonance. So it is due to the resonance that allyl carbocation is more stabler than alkyl carbocation, right? So resonance is the biggest reason. Now, third we will see phenyl carbocation. Take for example phenyl carbocation. Similarly, phenyl, tertiary phenyl will be more stable than secondary phenyl, should be more stable than primary phenyl. Fine. Primary phenyl. Now you can say nothing else but this is a benzyl carbocation. That means tertiary carbocation, tertiary phenyl methyl carbocation, phenyl methyl carbocation, that is benzyl carbocation. That means tertiary benzyl carbocation is more stable than secondary, which is more stable than. Now another one we'll see aromatic carbocation. Now I can say aromatic carbocation is much stable than benzylic carbocation. Aromatic carbocation is more stable than benzylic carbocation. Why? You can say it is nearly 10 raised to 11 times more stable than phenyl, methyl or benzyl carbocation. right? But because aromatic carbocation means there will be many aromatic structures. That means by resonance, right? Resonating structures will be there. So more the resonating structure, more is the stability, right? So aromatic hydrocarbon is more stable than benzylic carbocation. Similarly, allylic carbocation will be more stable than alkyl carbocation. In both the scenarios, resonance comes into picture. Both the scenario resonance comes into picture. And second thing also, we know one something is known as 4n plus 2 pi electrons. That means the Huckel's rule. Huckel's rule of aromaticity. And so what happens due to this Huckel's rule of aromaticity and due to resonance, there is a complete delocalization of electrons in aromatic ring, right? That means delocalization of electrons or delocalization of positive charge, one and the same thing. Delocalization of the positive charge, right? So this is known as the aromatic carbocation, right? Now we will see in general stability of carbocation. This is very important. See, now, sorry. Cyclopropyl carbocation tertiary is more than secondary cyclopropyl carbocation, which is more stable than one, two, three, four, five, six, 7. Fine. So this is 1, this is 2, this is, sorry, some mistake in this diagram. So I will say this, this, this. So this is positive charge. This is known as the tropylium carbocation. Right? This is cyclopropyl, this is tropylium. Tropylium carbocation is more stable than triphenyl carbocation in tertiary, which is more than diphenyl carbocation. Which is more stable than Now this was, now we have ended here. Fine. Once again I am writing it here. Phenyl CH2 plus. The stability of benzyl carbocation is approximately similar to allylic carbocation. Allylic carbocation and benzylic carbocation. Allylic carbocation and benzylic carbocation are near about same. Stability is near about same. And similarly, the allylic carbocation is near about same to tertiary. I'm saying near about same. I'm not saying exactly same. Fine. If I want to say, then I can say allylic is slightly more, but it is the value stability is near about same it is. So tertiary is more than this, clear cut I can say tertiary is more than secondary. And then this is more than primary, and this is more than CH3, which is more than CH2 double bond CH plus. Fine, make a note of it. We will see cyclopropyl tertiary, secondary, then tropylium, then triphenyl, tertiary phenyl methyl means tertiary benzylic, secondary benzylic, and primary benzylic. Similarly, you can say primary benzylic is somewhat similar to stability is somewhat similar to allylic, which is tertiary, right? So now second, but tertiary is more than secondary, is more than primary, is more than methyl, and that is more than alkene carbocation. Fine. Now, also one more thing is that in order to achieve stability, carbocation do undergo adjacent movement of some particular functional groups or particular atoms, so that they can be converted from one type of carbocation to the other type of carbocation. That means a tertiary carbocation, if it's possible that it can get converted to a secondary carbocation, then it will try to go in that form, in that particular fashion, such that the reaction will happen in that particular fashion, that the secondary carbocation becomes more prominent. I'll show you by example. Take for example CH3, CH2, take for example CH, this is H and this is CH2. Now this is nothing else but a primary carbocation. Now there is a, it's possible that you can also, this you can write like that, right? Because a bond can also be written in a double bond form, CH bond. So I can write CH3, C, CH2, then I can write CH double bond, CH2. Now the double bond will come out here, right? So now this here it was a primary carbocation, now here it is a secondary carbocation. So can I say secondary is more stable than primary as from this particular our stability chart? So the reaction will try to become, the product will, so suppose as I have told you this carbocation is an electrophile and it will react with a nucleophile. So suppose when a nucleophile approaches, so since there is a possibility of shifting, you can say shifting of hydrogen atom shifts from here to here, shifting of hydrogen. So the product formation, the nucleophile will go and try to attach on this carbon atom. So it will form a nucleophile and double bond, sorry, not CH, C double bond CH2. So it will form this compound, not this, not nucleophile will not be attached here. Here the nucleophile not get attached because it will be not be a stable product. Here it will be a stable product. So there is nothing else but I can say a shifting of hydrogen. So such type of shifting is known as 1,2 hydride shift. Hydride shift. 1,2 hydride shift. Hydride means hydrogen. Hydrogen, shifting of hydrogen. So shifting of hydrogen results in formation of a secondary carbocation from, and similarly whenever there is a chances that a tertiary carbocation can be formed due to the shifting of some other hydrogen, then quite possible then some other, then again it will not form a secondary, then it will form a tertiary carbocation and the nucleophile will react with the tertiary to give a stable product. Maybe that some amount of impurity of secondary carbocation product can be formed, but majorly the equilibrium will be towards the tertiary carbocation, right? So this was first type of shift, is known as hydride shift, 1,2 hydride shift. This also leads to the stability of the carbocation. So this is also one of the factor why this happens. Now the fine. Now we saw 1,2 hydride shift. So 1,2 hydride shift. Now similarly, suppose no, this is again a primary carbocation, but this is a tertiary carbocation. Now when a nucleophile has to come, the nucleophile will come in the later scenario. First there will be a rearrangement. In this case, as in the previous case, there was a rearrangement of the hydrogen atom. Therefore it was known as hydride shift. But in this case, now there will be a rearrangement of this particular methyl group. This methyl group will get shifted here. So this will become CH2, CH3. So this will be 1, 2 methyl shift or methide shift, whatever. Somewhere it is written as methide ion shift or 1, 2 methyl shift. 1, 2 methyl shift or 1, 2 hydride shift. So 1, 2 methyl shift will give a tertiary carbocation. It will give a tertiary carbocation. So the nucleophile will come and sit towards the tertiary carbocation, right? So 1, 2 methyl shift. So that will also lead to the stability of carbocation. Now the another type of this is reactive species is known as carbanion. Now as I told you previously, there was breaks the carbon atom, the electron remains with itself. And also the electron of the, now these are the three, and the electron of the hydrogen of the this G also stays with carbon, right? That means it has an excess of electron, right? It has 3 bond pairs and 1 lone pair of electron, right? The the carbon atom C, its electron is with itself, and the bond has broken, but even though the bond has broken, the electron of G stays with the carbon. So that means it has 3 bond pairs and 1 lone pair of electron. That means I can say in all total it has 8 electrons. In case of carbocation it had 6 electrons. It had 6 electrons and a planar structure, right? And a planar structure. And in carbanion it contains 8 electron and a pyramidal structure. Pyramidal structure. How it will be? Take for example carbon, like that, and so 3 bond pairs and a lone pair of electron. Total 8 electrons. 3 bond pair and 1. So you have the bond breaks, the electron of G stays with carbon, right? And G departs. So it has a pyramid. So it is a minus charge, right? It is minus charge. That means I can say it is a nucleophile. As in the previous scenario, it was an electrophile, carbocation. This is a nucleophile and reacts with an electrophile. Fine. So carbon atom with negatively charged. is known as carbanion. Is known as carbanion. As we saw stability in case of carbocation, similarly we will see the stability in carbanion. Right? Carbanion will be suppose CH3 minus. The previous case of CH3 plus, this will be CH3 minus. Now, what are the reasons for stability? First thing, electronegativity. Electronegativity. I can say stability is directly proportional to electronegativity of the ionic carbon atom. The ionic carbon atom. Electronegativity of the ionic carbon atom. The most will be the stability. Take for instance CH3 CH2 minus CH2 double bond CH minus, then CH triple bond C minus. So I can say this is nothing else but an sp3 hybridized carbon atom. This is an sp2 hybridized carbon atom, and this is an sp hybridized carbon atom. So can I say the percentage S character is increasing from left to right, right? Because this is sp3, sp2 and sp, which is 50-50. So the percentage S character is increasing, right? Similarly, so I can say as the S character increases, so does the electronegativity. So I can also say the electronegativity also increases from left to right. Similarly, so does the stability also increases from left to right. So more the electronegativity, more the stability. Alright, that means more the S character, more will be the stability. Carbanion, in carbanion I am saying. Fine? Right. I'll take a new slide now. Right? Electronegativity is one of the factors. Now the second factor happens to be, can say, inductivity. Today we'll have a very short session because I'm not feeling well. That is why in the last week I couldn't upload a lecture. I couldn't upload because I'm not feeling well. So today also we'll have a short lecture time, right? Inductive effect. Now I can say, please do remember these formulas. Basically, not formulas. Basically, yeah. If you remember these small things, stability is directly proportional to the electronegativity in scenario of electronegativity. Then S character, more the S character, more the stability of the carbanion. If you remember those things, then you can attack any type of problem. Any type of problem, because first thing you'll have to see who is more electronegative. Is the group attached is more highly electronegative element is attached, then that means that is the stability, right? So I am teaching you the concept. You understand the concept, then you can solve any type of question. Inductive effect. Stability is I can say it is inversely proportional to 1 upon plus I effect. Plus I effect. Plus I means electron donating. So stability is indirectly proportional to this. That means it is opposite. For example, CH3 minus, then RCH2 minus, then I will say RCHR minus, then I will say RCR and R minus, right? So R is a electron donating group, this is, yeah, this also electron donating, this is also electron donating. So more the electron donating group, that means more the I effect, less is the stability. I can say the plus I effect is increasing from left to right, but the stability is decreasing from left to right, or also you can say the stability is increasing from right to left. So these small things, if you remember, it will be very helpful, right? No, that was that we saw plus I effect. Sorry, inductive effect में we saw plus I effect. Now we will see minus I effect. Similarly, it's the same thing. Stability is directly proportional to the minus I effect. Right? CH2 minus, I can say BrCH2 minus and ClCH2 minus and FCH2 minus. I can say the minus I effect, I mean minus I power, you can say. The minus pi power increases from left to right, right? So does the stability, right? So more the electronegativity, minus I effect, more the minus I effect, more will be the stability. Fluorine is the highly minus I effect, means it pulls the electron, I is the least, which is, so does the stability, right? From left to right, right? Now the another this delocalization. First we saw electronegativity, then we saw inductivity, and now it is delocalization. Delocalization, or you can say even resonance. Now I can say more the delocalization of the negative charge, then more the stability. More the stability. More the delocalization of negative charge, more will be the stability. Take for instance CH2 double bond CH dash CH2 minus. You can say phenyl dash CH2 minus. You can say phenyl twice CH minus, then phenyl thrice C minus. Now you can see the number of resonating structures increases from left to right, right? Number of resonating structure is increasing from left to right, so does the stability. Stability increases from left to right, right? Stability increases from left to right. So more the delocalization, more the stability. So I can say that we have done 3 points for main points required for our stability, right? And there are still more couple of points or so that we shall do it in the next lecture. Just have a close view of all these topics, all the topic which I have taught you today, right? The remaining another two to three points are there which I'll take you in the next lecture, right? So I shall take a leave now. I hope you have understood this. I just request you to go through all these topics and all this, and as I'm going forward, you are getting a deep knowledge of the basic chemistry, basic organic chemistry, and this will slowly lead to our reaction mechanism and the reactivity. Why does the reaction takes place? So I shall take a leave. So prior to leaving, I'll just request you to please follow me on Facebook, and do comment and subscribe my channel on YouTube. And you can also Twitter me or send me an email or an WhatsApp. All those addresses, and I have written in my description, in my description box. So please look at this. Right now I should take a leave. So I shall meet you in the next lecture, lecture 12, right? Where I'll be explaining you all the different some more reasons for the stability of carbanion, right? So I shall take a leave so that you can also and go through these chapters completely, right? So I will meet you in next lecture. Thanks a lot. Thank you. Namaskar.